Okay, hi, we're FGC Team 7477, the robotics team in Oviedo, Florida. And we compete in the first Tech Challenge League. I'm a programmer on the team. This is Mernal.
I'm Renal and I'm also a programmer.
So would you like to start with introducing yourself and what you do? Just
Sure. So let me share the presentation that I made, and that way you could see also some of the research that we have been doing. Okay. Hello, everybody. This is Shaurya. I'm assistant professor in UCF. Currently, I'm working in civil, environmental, and construction engineering department. And this is my brief bio. I did my PhD in electrical engineering from University of Nevada, Las Vegas, and I did my postdoc from NYU. My work area is in future cities. So I'll discuss more about what do we call future cities and smart cities and urban transportation, all that. We'll go into specifics. But on a very high level, I do research in data-driven dynamical systems, game theory, systems modeling, and all of these are tools and techniques which are applied towards smart cities. Towards the teaching, I uh, taught courses in cyber physical systems, Internet of Things, and standard control theory courses.
so
Over to you. Yeah.
yeah. So if you just would like to maybe talk a bit more about like the projects that you've been working on and things.
Sure, sure. I can do that. Um, so let's keep going because this presentation will have all the details. So this is an introduction to my lab. We call it Urbanity Lab, Urban Intelligence and Smart Cities Lab. I have four PhD students working on different areas, with different expertise: machine learning, V2X communication, lidar perception, modeling, and control. These are some of the past members and undergraduate students. So I wanted to talk a little bit about the Future City Initiative at UCF. Essentially, a more detailed name for the smart cities. So around 2018, UCF, particularly Civil Engineering Department, took this initiative of uh, of creating this interdisciplinary view of how our cities would evolve in future, how to make them more robust, resilient, by using technology, by harnessing technology. When we say technology, you can think about the sensors, controllers, cameras, lidars, noise sensors, acoustic sensors, and all of that, and how you can run your city more efficiently in the given resource. Right, land is scarce, roads are scarce, but within those limits, how you can increase the efficiency. Along that lines, we have started an MS program in smart cities, which is one of the only programs in the country which focuses on the technology that are needed to create smart cities. Now, let me talk about some of the research directions, particularly that I pursue and my lab pursues. So, first of all, let's talk about the bigger picture. So, you may have heard of the term cyber physical systems. Now, what is cyber physical system? Physical system. So, if you talk about a building, a building, and let's say it's, an engineering building. It will have a lot of classrooms and building and labs and students and professors and researchers. All of them is a system. It's a physical system, right? Or you can take an example of the roadway systems, right? So the physical infrastructure, that means the roads and the vehicles and trucks and everything together is a system. Now, what is cyber physical systems? Now, when you talk about computation plus networking plus physical processes, that means you have sensors on the road, cameras, detectors. They are collecting the information, and then they are all connected to each other. They pass on the data, and then they process that data and do some computations. Let's say a control algorithm, how the red light and green light should change or adapt to traffic conditions. Together, we call it cyber physical system, which is the interconnection between the cyber world and the physical world. and it has applications to multiple domains: healthcare, transportation, smart cities, power grids, aviation, agriculture. It's a different application areas, which existed even before this technological leap. For example, transportation was there, healthcare was there, but now we are talking about how these cyber components would interact and make the things even smarter, right? So it poses a lot of challenges. For example, in sensing, observability, sensor placement. Where do you place the sensor so that you get maximum information from the sensor? How do you create accurate models, control actions, networking, data management? Sort of all these three, my focus is on solving these three challenges, which is sensing, modeling, and control. Now, I will not go too much into detail about, so this is one of the theoretical domains that I explore, which is called synergy between micro and macro models. But this is very interesting to you, I think, and your audience. So I'll explain a little bit in a very, layman's language. Now, when we talk about modeling any system, you can model at different scales, different temporal scales, and different spatial scales. Now, think about the traffic when it flows on freeway, right? You can model it as a compressible fluid. That means, a fluid is flowing. Now, what first principle or physical law you would use to model it? You can model it using conservation law. That means no vehicles would be created on on a section of the freeway, or it would be destroyed. Right? They cannot just disappear from the road. That means using the conservation law, you can create a macroscopic law of the traffic flow. Macroscopic means that we are taking a macro view of the system, whereas the micro view would mean that you are treating and modeling individual vehicle, how I drive my vehicle, right? It would come from a different physical law or physical understanding. Let's say if we are driving on a one single lane and you are driving in front of me, then my driving behavior would be dependent on how you are driving, and I want to maintain a safe gap between my car and your car. So that kind of car following model will be developed, right? So the first thrust that I do is I use mean field games to actually establish a relationship between the micro scale models and the macro scale models. And using game theory, what is game theory? So for example, um, I would interact if there are, let's say, 10 players in any game, then I would interact to all the other players. That is classical game theory. However, the mean field game, so what it says is you can aggregate the behavior of all the other agents, all of the other players, and then I would react to the aggregate effect of the other agents. I'll be happy to do a follow-up presentation and going deep into these topics, but I think I'll just move forward for now. Second one is synergy between physics and data-driven models. Now, this is also very interesting, and I think your for your audience also, especially I think the high school and the futures scientists and engineers. What is so we talked about micro models and macro models in the previous slide. Here we are talking about the physics models and data driven models, right? Everybody must have learned about machine learning, and machine learning is trained using data and models and so on. But before all of this, right? So this is let me point here. So this is a typical evolution of an epidemic. So we call it SIR model, a very simple model developed probably centuries ago. I think the first case of plague, which was captured in UK and then modeled. So it's susceptible, infected, and recovered, right? So how a pandemic, for example, COVID-19 spread. So what it says is, the susceptible population, which is, the 100% population, would go down, and the infected population would go up, and then finally go down, and the recovered population, everybody would be recovered. So this is how, the a disease would spread in the community. Now, how we would model it is using differential equations. That means this is a physics-based model. We have equations. We know how systems would evolve, and we would have parameters and so on, right? So we are modeling the system by so this is called a top-down approach, that we have a top-level understanding of the system, how it's supposed to behave, and then we write few equations and then see if it works well. However, the complex systems, especially today, you cannot apply physical laws. Sometimes you just don't have physical laws for that complex system and so many moving parts. So what do we do there? We do data-driven modeling. That means we collect the data from the system, we observe the data, and this is called top-down bottoms approach. That means using the data, we try to build models, right? So now, the research question that I investigate is, how do you create the synergy between the physics and data-driven model? Now, I should mention that I'm not saying physics-driven model is good or data-driven models is good. Both have their advantages and disadvantages. Physics-driven models, come with nice equations and greater level of understanding and confidence, but they cannot explain everything what is going on. Whereas data-driven models are kind of black box models, so you understand the data, but what if you observe the data in another city, in another planet, whatever, you cannot. So there are issues, and these are specific to also, specific challenges to machine learning as well, like transferability of phenomena and so on. I can go on, but let's cut off here. Parth and Mrinal, you feel free to ask any questions in between if you have any.
Um, hmm. So, what are some of the applications of the synergy between physics and data-driven models?
Great.
Maybe answers both
No, it's
sides.
a great question. So, for example, data-driven models are data hungry, right? So they need a lot of data to actually. So one application is if you infuse some understanding, which is essential to physics of the system, into data-driven models, then it becomes a hybrid approach, right? So some of the deficiencies of data-driven models can be overcome by that. Uh, and then when we call about the synergy, it's like two different modeling regimes, but one is depicting another view of the system, one is depicting another view. Which one would you take, right? So once you have an understanding and kind of a consensus between two regimes, you will have a better understanding of the system, especially the complex system, and then you can design intelligent controls. Essentially, modeling, next step or the end goal of the any good modeling is to control, right? We want to optimize our system. Let's say there is an epidemic, and then you want to allocate your resources, for example, your hospital beds, your vaccines, your healthcare professionals. So it's a big system, you want to optimize and control it efficiently. But before that, you need to understand your system, how it's evolving, what will happen if I do this, what will happen if I do this. So this inherently is captured in the model engine. Make sense?
I guess I have one more question about
Yes.
this topic. Like, I know like big I guess counter argument to a lot of like AI driven solutions is that you don't really know what's going on behind it, like you mentioned. Do you think this type of synergy would solve that issue? Like, people can now tell what exactly is going on behind these models, so they can, trust it or check what it's doing to see if it's actually using a process that they agree with.
I think that's a great question, Mrinal. And this is exactly where the research community is currently. That we know, the machine learning is great. Chat GPT is here. It works. The computer vision algorithms can detect. They can work. However, is there a guarantee it would always work? No. The autonomous driving is a very good example of it. So, especially we are hesitant in applying these machine learning AI tools in safety critical scenarios. We cannot rely yet because we don't know what is the edge case. So, for example, you might have seen a video of a tire, I think flying on a freeway, and then one of the autonomous vehicles did not, it was not trained for that particular data instance. So it was an edge case, and it went blank, right? What to do in this scenario? Whereas when you talk about, let's say, a more physics based approach, more reasoning, human logical based approach, it would probably will be able to reason better, okay, how it would happen, right? So I think it's a great question. Go forward, and there, that's where the research community is looking to, is interpretable machine learning or interpretable AI. Can you explain how ChatGPT works, right? I mean, it's, yes, it's a billion parameters in there, and big neural network train and so on. But what if this happens? What if this question it fails? When it fails, and why it fails? Right? So those questions.
Right.
Okay. Any more?
Yeah, this
More people with
so
questions.
if you want to start with the now question, so I know that a lot of this like talks like deep learning and stuff like that. We kind of learn to touch on it in FTC also with like models and computer vision and stuff and how we go about that. So do you see many applications that the people learn in robotics maybe transferring to like this field of research and stuff?
Yep. So, for example, I think robotics is a very nice area, and I have seen it evolve over the years. Like previously, it used to be very confined to the control community, the modeling and control, and it was more mathematical. Like I mean, traditional approaches. Let's call it traditional approaches, like physics-based modeling approaches that I'm talking about, like Kalman filter and stuff, and then you would plan optimize it based on JB equations, optimal control, like path planning. If you are to go from point A to point B in minimum amount of time, minimum distance, so on, you would optimize and do all these things, model driven kind of approaches. However, recently, with the advances in machine learning, now it's even more data driven. For example, reinforcement learning is a great tool for making those decisions. Computer vision, and lidar perception, these things provide enhanced perception of the system. So even the modeling and control and planning, these kind of things are coming from reinforcement learning, hidden trial kind of approaches, genetic algorithm. So I see a shift, and I think robotics is a very nice area to work if you have, and it allows you to actually use tools and techniques from multiple domains, right? Traditional modeling, control theory, AI, machine learning, and all those things. Even computer vision has established itself as a field because of so much commercial interest, and so much commercial products are there. So it's a rapidly emerging field. Um, and one more point I need to add is the swarm robotics, right? You may have seen a swarm of small robots or a swarm of small UAVs, doing a complex task together. So they are actually what I called here, the synergy and the interaction between the agents, right? So, for example, there can be kind of a competition and cooperation between the agents. Like all the small robots want to do it collectively, but they also want to maximize their individual payoffs. That I want to do this or contribute more, but they have to do it sort of cohesively, and keep making that formation towards that task, whatever that task is, right? Retrieve a mine, retrieve a bomb, or whatever. So those kind of interactions between agents, and defining their individual value functions or cost functions, and the overall macroscopic behavior, I think these kind of new technical advancements have given new challenges and interesting problems to work on, more both theoretical and also practical. Okay, move forward.
Yeah, sure. So maybe some
Go
more like
ahead.
sorry. Yeah, so maybe some more non-technical questions now. I think to be successful in robotics, we need people with like we need people doing their jobs, but also they need to be communicating well to do that. So, would you want to talk about maybe how you use communication in your research on a day-to-day basis to be successful?
So let me understand your question. So you're saying communication on the day-to-day basis to be.
Like maybe plans like how you talk to different people, maybe weekly meetings, something like that,
Yep.
to get your
So I
tasks
think
done.
it's a good question. So basically, when you're doing research, right? So you have some vision, you have some hypothesis that okay, if we, for example, incorporate physics into the deep learning or machine learning things, we would have some improvements in, let's say, the training performance, the computational complexity, and so on. So we have a vision, but will it work? So it's so research is kind of very different when it comes to a usual, let's say, a company job where okay, I'll be able to program this web page. I know how it will be done. I'll create a version one, show it to my colleagues, get some feedback and improve it, add some functionality, and it will be done by the end of 1 week. I know it will be taking that time. But when you come to research, you don't know, right? It may be done in 1 week if you're lucky, or you may get stuck to a problem which you did not even anticipate, that okay, I'll be stuck because of this problem, because I have insufficient data, my model is not converging. What do I do? So you have to constantly kind of evaluate your strategy. And then communication is key here. So when I communicate with my students, undergraduate students and graduate students, we do a weekly meeting, and usually they create a presentation, and then they present what they did, what they found out, what worked, what did not work, because that's also very important, right? Sometimes what students do is it's easy to get depressed or say okay, it did not work. But that is not a good word, it did not work, right? I want to see what you did and how you approached it, and you failed it, so we can as a group discuss that this might be the problem or that might be the problem, and how we can evolve from it.
Yeah, I think that's what we try to do in robotics also. When like maybe some of the new members aren't able to do something, we try to break it down for them, make sure they learn how to do it so they can do it for future. Simranal, would you like to?
I also have questions. I know in research there's a lot of uncertainties. Like you guys can, like you said, you guys can get stuck at some problem that may not be resolved for some amount of time or maybe a long time. How do you usually plan out these research projects that you don't necessarily know how it may end up turning out?
Yeah, I mean, that's a tricky question. So we make a lot of plans, and then we make a timelines, and we'll try to finish this by this date, but usually they don't work. And then it's not a good idea to actually enforce them like a strict timeline, because you cannot, right? I mean,
Hmm.
um, research is more about exploration and progress. Sometimes you are trying to find A, and in that objective, in that pursuit, you find B, you find some other challenge. So that also has a contribution, as a research community welcomes that contribution, and proudly whatever I created as B would serve as a foundation to get A. Maybe some another researcher would take it there. So planning wise, we do plans, we do have some ideas that okay, we want to achieve this in this semester, but it's not possible to enforce that okay, we need to be done by this paper by this timeline. It's just not feasible.
And then, does your team often like involve people working together with different skill sets? Like, is your research interdisciplinary?
Yes. So let me answer, but I got a. I was thinking about one more point on your previous question. We also work on very some sponsored projects. For example, from Florida Department of Transportation or some private agency, there we do have strict timelines, right? Fixed projects, 2-year project. For example, to do implement, let's say, pedestrian safety applications and test and all that. So we do follow timelines, that we will develop this in this time frame, and we will test it out. So yes, there are some open-ended questions that cannot be timeline, but when it comes to implementation and exploration of the data and getting insights, all that we follow the strict timeline. Now, coming to your question, sorry, I forgot.
Oh, right. Is your research interdisciplinary?
Interdisciplinary, yes. A great question again. As I introduced myself, I have degrees in electrical engineering and mathematics. My application domain has always been transportation, because the smart transportation is one area which is very, very interdisciplinary. In fact, most of the areas are getting very interdisciplinary when we talk about any real world app, even robotics, including robotics. So, um, so for example, when once you talk about technology, so you have cameras, you have lidars, you have so you need, for example, the electrical engineer people for hardware and understanding the communication between vehicle to vehicle. You need to understand that, to have control engineers who can design control algorithms. You need to have civil engineers who understand how the traffic flows, how to optimize, what would be the effect of a road closure versus putting a stop sign here versus there. So I think it's an interdisciplinary group, and in my group also I have people from computer science background, from electrical engineering background, from civil engineering background, all doing work together, on different aspects of the research.
So how do you like how do you try to facilitate, like, I guess, effective communication between, say, somebody that's proficient in machine learning and somebody that's proficient in electrical engineering, and they need to work together, like, even though they might not understand the topics that they're actually working on technically as well as the other, how do they still work together efficiently
Yeah, I
together?
think another very important point. I think it comes with experience, and I think it's probably on the manager, on the team leader, or for example, in my case, the lead researcher. So usually I have to switch very quickly. The vastness that I showed in my team, and also the kind of work, somebody's working in physics-based models, somebody's working in data-driven. I could not show the slides on the lidar perception and so on. So all of them are vastly different fields, right? So when we do discuss these things, um, as a researcher, I have to adapt very quickly and understand the domain. So it's like an art that you develop slowly, that you get the big picture, right? One person cannot be an expert in everything, but do you get the general idea? And math is sometimes very useful, because behind all these machine learning algorithms, essentially it's mathematics and optimization, right? How do you obtain a function that generalizes from this data distribution to to a function, right? So if you can connect those dots, then basically you see, oh, in a sense, it's this is what we are doing, right? And then if we do this, then this is the mathematical structure we need to follow. So it helps. Mathematics helps in understanding different pieces, although that in different language, different things happening. But I think at an early age, it may become challenging to actually understand everybody else's work. Although I kind of try to promote this, that everybody understands everybody else's work. That's why we have group meetings, so that a person working in pure mathematics even sees some elements of machine learning and gets that exposure. You don't know, whatever you are listening is sometimes going in your subconscious, and then when it's needed, it comes out automatically, right? Yep.
So I had one question about like a big part of your research is data collection because all those like models and everything they need a lot of data to like train them and everything. So how often do you find yourself having to get new data, or like how often do you find yourself having to collect new data and things like that?
Yeah, very good question, Parth. So data collection and having good data is critical. Whether you are taking a more classical physics based modeling approach, control approach, or even the new one, it's even more critical with these new approaches. There is a new saying people call, there was a buzzword, big data, a few years back. Now they say good data is big data, right? So instead of creating huge amount of data which you don't know if it's well screened, if it has a lot of anomalies, missing points. So if you have well curated data set, it can serve well. However, data is always a challenge. Data is always a challenge getting good data. So for example, in the machine learning community, we have some benchmark data sets, and that's probably you have some experience in. So the annotations that we create is creating towards a label data set, and then we can open it for the research community. Some of the things that we work on, for example, connected and autonomous vehicles, how they would interact, and based on those information exchanges, how the traffic flow would be affected, right? So we can, for example, only take a guess because the data is not there yet. I mean, large scale implementations of connected vehicles and their interactions and are not captured yet. So sometimes we do synthetic data creation. That means we generate the data through simulation. So we have a transportation layer where micro simulation of vehicles is happening, and the communication layer where the communication exchanges are, and based on that we know how the communication evolved and how the vehicles evolved on the road, and then we can use that to do some surrogate modeling and so on. But data is very important. Good amount of data, accurate data for all the work that we do, and it's sometimes very challenging to get good amount of data.
I have another question about it's more technical about your research. I know that you mentioned physics-based models, and I know that usually, like generally, like deep neural networks or just like data-driven models are just more widely talked about. Um, what like is the issue with physics-based models? Is it because they only have like very specific use cases, or is there some reason why just neural networks are they tend to be a lot more popular than
Hmm.
physics-based
So
models?
the limitation with physics-based models is that you don't know the physics of everything. For example, whatever buildings you are in, let's say a house or a hotel or a building, right? So, for example, the energy consumption of that building, let's say, is dependent upon how people move in, move out, and all that. So, but creating a physics-based model out of this, you would, and it's a now complex system, right? So, a lot of people, and there is a stochasticity involved in terms of your user behavior and so on. But when it comes to data, that means you provide a time series that okay, this is how the consumption, electricity consumption in that particular house changed over the years, over months, right? Now the the neural networks have become so powerful, or neural network is just one approach, and then modified, for example, cnnns, lstm. So for particular application, for example, time series prediction and modeling, lstm is very popular. So they can capture from that data and then train itself, and so that's one of the reasons, uh, especially in complex systems. If it's a small system, for example, a spring mass system that you may have seen, right? So you have a spring, you have a mass, and then so you there is a governing physical equation. You can explain the phenomena with some equations, but with larger systems, you just cannot.
And then another question is more of a soft skills type of question. How do you deal with setbacks in your research?
We do have setbacks. We do waste time. For example, our hypothesis, for example, this could work, and then we work for 6 months and it did not work, right? So it is a setback. I mean, because we wasted 6 months, we did not get in the research outcomes we wanted to, especially for the student, because they want to finish in time and publish papers. Um, so usually we take it as a learning. We try to motivate ourselves that okay, not knowing something is also knowing something. That okay, this particular thing did not work, right? But I'll give you a particular example. So we were training this physics informed deep learning approach for traffic state estimation, and then there is an algorithm called particle swarm optimization, and we had this hypothesis that this could work great for training this PIDL, physics informed deep learning architecture, but it did not work. And it and then we contacted, for example, some of the other researchers who were showing good results on that, and they were publishing papers. And when we found out, and they admitted that, they are, some of these algorithms are very sensitive to some of the hyperparameters that you initialize during these trainings, right? So it's also an art, right? That means it's not that I'll give you a model and it will work on your data, right? So it will have to be kind of how you start it, how you initiate it, and so on. So if it's that sensitive, what is the application of that particular algorithm? So we learned that this particular algorithm is very sensitive. So we kind of reported that in our next paper, where we explored another algorithm which worked.
Yes, Murnau, do you have any other questions?
Yeah, I guess just another like general question about AI. Where do you see, I guess, AI going in maybe like a decade or something, or as AI becomes better and better? Do you think there are certain, I guess, areas where AI should not be used, like maybe in AI based lawyers, or like handing out prison sentences based on AI, or something like along those lines?
Yeah, I think that's $1 million question, right? Everybody is asking where is AI heading, and where should we use it, where we should not use it. And based on the history, so there are two views. If you see the research community, one view is that it is safe. One view is that it is not safe and it can go out of hands. I mean, I will take a balanced approach, and I'll say yes, there is a need for caution, and how we train, because these things are powerful. The kind of reasoning, if you have used, some of these new tools, the kind of reasoning that they can do, and amount of information it can generate, and the context it can understand, it is only going up from here, right? It's not going down. So. Uh, Based on the history, what I see is humans are quick to adapt. The internet age, the Google age, and all that. So I think we would adapt. There'll be huge changes in how we work. I think one of the things that I can say with certainty is our efficiency is going to be improved, multifold. That means, for example, a programmer, if he was doing something in a month, he'll be doing 10 times more, 5 times more easily. How that would affect the society in a whole, some jobs will be changed, the realignments of the job will happen. But at the same time, it will also create new opportunities and new job avenues. I think the ones who would adapt quickly to it will come out, will be ahead of the curve. At the same time, uh, for example, in teaching and learning, how do you ensure that students still learn some of the concepts and the rigorous process? So a lot of adaptation, I think, will be needed in all of the fields, in the medical field, and the legal field, the education field, the research field. So I think it's an interesting times ahead. Yeah.
That's all the questions I had, Parth. Do you have any more?
I think that's all the questions I had. I think we learned a lot from your presentation, and it's good. And as a robotics team, we're really trying to get more people into this field. Like we're we're like we're introducing, we're trying to start more teams in like local elementary schools and stuff. So this is like a good learning opportunity for everyone that's like we're trying to introduce to it. So thank you for taking the time to do this, and
Of course, my pleasure. It was pleasure talking to you, and I'll be